So let us first go through what are the different topics that we are going to study and to what extent. Right? So we'll start with theories of failure. Theories of failure. So this is what we will start it today, right? Then thereafter, design design against fluctuating load. I hope whatever I'm writing, it is visible. Fantastic. So thereafter, we will do riveted, welded, and threaded joints. Bearings, clutches, and brakes, gears, lastly springs. Right. So we have in total of 5 lectures. Multiplied by 2 hours approximately. So we have 10 hours to complete the 7 chapters. Right? So we will do it according to the time available to us. Right? So let me see how much time approximately you'll have to devote here, right? So theory of failure is not a very big chapter. It is a transition from strength of materials to machine design. Just hold on, guys. Give me 1 sec. So you can note this down once. So as you can see here, machine design is not about designing of machines, but basically what we are going to see, design of machine elements. So that is a better name to this subject. No way we are designing machines, what we're going to design, what we're going to see is design of machine elements, right? For example, the gears, clutches, brakes, bearings, springs, all different types of joints. These are not machines, this is just machine elements, right? So we are going to see the design of machine elements. Okay. Just hold on. Okay. So today we are going to start with theory of failures. Just hold on. I'm just getting adjusted. Just hold on, guys. Sorry for the trouble, everyone. Just I'm trying to make some changes. Okay. Okay. Sorry for the delay. So I hope now it is visible to everybody. Please give me a yes. It's still there. Okay. So sorry for the delay. So the WebEx has changed a bit since the last time I have used it. So I faced a little bit of difficulty in starting the class. That's okay. Now things are smooth. We'll go smoothly. So as I told you, what are the different? So if you have any, I'm simultaneously going through the chat. So if you have any problem, any doubt, anywhere, right? So ping me on the chat. So that is how I'm not putting on the earphones to listen if somebody is saying something. Preferably through chats. Okay. And if you want to speak after that, then I will definitely give you the permission. I'll put on the earphones and you can speak. Okay. So that is how we are going to do. So let's start. So theories of failure, right? So first, let us try to understand what exactly is theories, what is exactly is a failure, and why theories of failure. Why exactly you're going to study theories of failure, right? So you have studied strength of materials, right? You all of have studied strength of materials. Okay. Give me yes if you can hear. If it is true, you have already studied strength of materials. Let me see if all of you are active. You study strength of materials. People are there. It's going on. Solid mechanics, right? All of you, are you present? Aravindan, Guna. Yes, I can see Guna writing. Harini, I can see. Naveen, Pravakar. Are you there? All of you? Yes, Prabhakar, Ravindan, Naveen. Good, fantastic. Okay. So do keep on chatting in between so that the class is a bit interactive. It is not going to be a one-sided class. It is going to be something interactive. Okay. So do keep on typing on chats. Okay. Otherwise, it will get boring. You'll feel sleepy. That is not something I want. Okay. So what is the difference between strength of materials and machine design? In strength of materials, you study the basic equations, basic theory, the basic uh, set of tools. What is strength of materials? It is the basic set of tools, right? You create a set of tools for yourself so that you can now apply those tools while designing of machine elements. So in strength of materials, you have studied all different equations. Yeah, I'm sharing it again because of some reason it got stopped. Okay. So in strength of materials, you have studied the basic equations. Okay. So I hope you this chapter, theories of failure, is a transition from strength of materials to machine design. Some people consider it in the subject of strength of materials. Okay. So we will be teaching you in machine design. Right? So let us first try to understand what exactly is a failure. Okay. What exactly is a failure? Okay. So if I talk about failure, right? So whenever a material is stressed beyond the elastic point, and if there is a permanent deformation, then we can say the material to have failed. So, आप बताइए मेरे को, you tell me one thing, ठीक है? You studied the stress strain curve, yes or no? You studied the stress strain curve. Naveen is saying yes, right? Good, right? So if you see the stress strain curve, my dear friends, so what is there in stress strain curve? I'll draw a simple stress strain curve here. For a ductile material, right? So there is a proportionality point, elastic limit, then yield point, right? Then lower yield point, higher yield point. Then you have the ultimate. Then you have the fraction limit. Can you tell me what kind of material this stress strain curve is representing? Is it ductile or is it brittle material? Is it ductile or brittle? I hope you can see it. Is it ductile material? Yes. Naveen is responsive. I'm not very sure about others, but this is a ductile material, right? You can see because of the yielding that it has undergone, right? Now, somewhere here lies the yield point. All of us know somewhere here lies the yield point. So what happens after the yield point? What happens after the yield point? After the material is strained or stressed beyond the yield point, there will be plastic deformation. There will be plastic deformation. So what does it mean by plastic deformation? Means it is not going to come into its original shape and size. What is the difference between plastic and elastic? What is elastic? What is elastic? Elastic means, what is elastic? Elastic means that if you stress it, if you apply some force and if you deform the material, it is going to come to its original point, original shape and size, right? So if you cross the elastic point, okay, yes, retain its original size. Yes, retain its original shape and size, right? It will come back. But if you cross the elastic point, it is not going to come back to its original shape and size. So we say that some amount of plastic deformation has taken place. We say that some amount of plastic deformation has taken place. Now, my dear friends, the yield point you are looking at, yield point and elastic point, they are almost the same. The yield point and elastic point, they are almost the same. In most of the materials, it is exactly the same point. Okay, so you call it a yield point or you call it the elastic point, doesn't make much difference, right? In many books, if you go through, there is no separate mention of elastic point, right? It is the yield point. That is also saying the proportionality point, right? And the elastic point. Okay, all three we are going to consider the same here, right? We will tell it as yield point. We will deal it as yield point. Okay. Now, let us take example of a simple machine element, like for example a gear. Okay, आपके पास एक गाड़ी है, you have a car and you have fitted, there are a lot of gears inside the car, right? So if suppose because of some mishappening, okay, the gear, one of the tooth of the gear, right? One of the tooth of the gear, it is overloaded. If I'm saying overloaded means the forces are such that the stress goes beyond this point. The forces are such that the stress goes beyond this point. So if the stress goes beyond this point, the material will get strained beyond this point. So some amount of plastic deformation will happen. So once the plastic deformation happens, because why? Because the stress has gone above the yield stress. So some amount of plastic deformation has happened, right? Now there will be no regain of size, right? It will not retain its, it will not come back to its original shape and size, right? Now a gear tooth which have been plastically deformed, it has changed its shape. Do you really think that it is going to do the necessary activity, the task for what it has been designed for? Yes or no? If the gear tooth is the teeth of a gear, it gets deformed. Suppose you said this should have been the teeth of the gear, right? It gets deformed. It gets deformed in whatever manner you say. Suppose it becomes something like this. Do you really think that it is going to perform its necessary duty for which it was designed for? Yes or no? I hope people are online. It is still going to perform. You feel it is still going to perform its duty, even if the gear teeth it gets permanently deformed. Even still, it is going to perform its duty properly. My dear, if the teeth get deformed, the velocity ratio will not be fulfilled. If the teeth get deformed, the gear teeth has a very close tolerance profile. You cannot just have any kind of profile. You learn about in theory of machines, you're going to learn about the gear teeth, right? So the gear teeth have a particular kind of profile, which is either involute or cyclodal. You learn what is involute cyclodal, right? If even a slight deformation is there, even if there is a slight deformation, if it changes its shape, it's no longer going to fulfill the law of gearing. If the law of gearing is not fulfilled, what will happen? The constant velocity ratio will not be able to maintain. If the constant velocity ratio is not maintained, that will lead to problem to all different parts of the engine, right? This kind of vibrations, the vibrations that it will produce, the sound that it will produce, the heat that will be generated because of this, small chips will come out, right? From the gear tooth, right? Chips will go into the all different into the engine oil and all different parts, right? The heat will be carried out, will be carried to the other parts. The other parts will get heated up, right? And a lot of vibration because of which there will be a problem to a lot many things. Okay, so that's why okay, I'll say this screen again once again. Just hold on. That's why once the gear tooth it is permanently deformed, we will not be able to use a gear tooth again. So once the gear tooth is permanently deformed, we will not be able to use the gear tooth again. Right? So we can say the gear tooth has failed once it has been permanently deformed. We can say, can we say, the question to you is, can we say that once the gear tooth is permanently deformed, if it has been loaded beyond the yield point, if the gear tooth is loaded beyond the yield point, it is no longer serving its task. It is no longer serving its purpose, right? Can we say that the gear tooth has failed? Yes or no? I hope you are getting my answer. I hope what you're getting what I'm telling you, right? So the machine elements, basically what we are talking about is the ductile elements. We're not into brittle elements here, right? So all the ductile elements that we're going to use, okay, there are plenty of examples. You take the engine of the IC engine, the crankshaft, the crank, or anything else, any other thing, right? If the member gets permanently deformed, that is what I'm talking about is it gets a plastic deformation, right? It will no longer be useful. It will no longer be useful because it will not perform its assigned task function properly. So in that case, what we can say? We can say the material has failed. So the point here is, my dear friends, what you need to understand is, if I'm talking about failure, ये जरूरी नहीं है, it is not necessary that it is a fracture. What is a fracture? Fracture means the materials is getting separated into two parts, right? What is a fracture? Fracture means the material is getting separated into two parts. That is a fracture, right? But for machine elements, most of the machine elements will be designed using ductile material, mild steel, medium carbon steel, aluminium, and its alloys. But all the machine elements will be designed using ductile material. Can you tell me why? Why we are not using brittle material? Any idea? Or is it right? Or do we use brittle material? Easily broken, that's not right. The strength of brittle material is more than that of ductile materials. The strength of brittle material will be more than that of ductile materials. The thing is, brittle material does not give us a warning before failure. Brittle material does not give us a warning before failure. It is a sudden failure. See, this is a failure for a ductile material. What is this? This is failure for a ductile material. Okay? These points are very important with respect to objective, because PSU exams, okay, most of the questions you'll find will be conceptual and objective in nature. Objective in the sense one-liner answers, right? So these concepts are very important so that you can easily mark the answers. Yeah, we'll have a combination of both objective and subjective, but we'll focus on the theory part so that if your basics are clear, right, you'll be able to answer any question. Okay, and we'll also do a lot of to the problems to the extent that is necessary. Okay, so see, this is the failure of a ductile material. This is the failure of a ductile material, and you can see how much of warning it has given. It has given a lot of warning, my dear friends. It has given a lot of warning. पहले तो yield हुआ, right? Material shape and size has changed because of the yielding. What will it do? It will produce sound. Suppose, for example, you are driving a vehicle and it is making sound, cut. You know something is problem. Some problem is there. What you will do? You'll go to the mechanic. The mechanic will find out, sir, this is the problem. Your gear has, because of some excess load, okay, your this part has deformed, or this has become bad. This is permanently deformed. What you'll do? You'll change it. Right? Much before failure. I hope you have already gone through the stress strain curve. So I'm not focusing much, okay, on the stress strain curve. Much before failure. This much before the fracture. This is the fracture point. Which is the fracture point, my dear friends? This is the fracture point, right? So much before fracture, the ductile material has already given you the warning that something has gone bad. Now, if you take the stress strain curve of brittle material, it is very important to understand this. So only after understanding this properly, you'll be able to grasp this chapter. So what is the case for a brittle material? If you see the stress strain curve of a brittle material, the brittle material stress strain curve is something like this. और इतना भी deep नहीं आता. That's it. खत्म. So it will suddenly fail. You can see it will suddenly fail at this point. It will suddenly fail at this point. It will suddenly fail at this point. It will not give you any warning. The strength might be high. Okay, not for all brittle materials. I'm not talking about all different brittle materials, but definitely there are now the manufacturing science has undergone revolutionary changes. There are so many materials of so many different sizes, so strength, right? You can add lot many things to increase the strength. So definitely brittle materials are available with brittle strength. Okay, but the problem is it is not going to give you any warning before failure. Okay, so for brittle material, what is the fracture point? This is nothing else but the ultimate point. So while designing any part, anything, suppose you are designing using a brittle material. Suppose you are designing using a brittle material, right? Suppose you are designing using a brittle material. So what is the strength criteria? What is the strength criteria for a brittle material? It is the ultimate strength. It is the ultimate strength. So, brittle material, are you going to use brittle material? Generally not in machine elements, but still they are being used. Where? Brittle materials are used wherever the type of loading is compressive in nature. Brittle materials are used wherever the type of loading are compressive in nature. For example, you can say the bricks of our house, they're brittle in nature, right? Bricks are brittle in nature. The concrete that we use in building of house, they're brittle in nature, right? That's why the columns, you must have seen the overbridges, the columns used in overbridges, they're made up of concrete, brittle, right? So brittle material have very high compressive strength. So it can withstand compressive strength very much, but it is very poor in tensile. So we'll not use brittle materials in any machine elements where there is tensile stress, where there is tensile loading. Any amount of tensile stress, we are not going to use brittle materials. But if it is only about compressive stress, for example, the machine bed of a lathe machine, I hope you have seen lathe machines in your lab. The machine bed of a lathe machine is made up of cast iron. Cast iron is a brittle material. Why? Because it is compressive in nature and it has some other properties like it easily absorbs vibration, right? So you are going to use, definitely we are going to use brittle material, but only where the nature of force is compressive in nature, right? Why we are not going to use it in machine elements? Because two things. First, it cannot withstand tension. Tension में बहुत खराब है. Brittle material will fail very badly in tension, right? Secondly, it does not give you any warning before failure. We don't want any kind of material which is not giving you any warning. Just imagine you're sitting in a chair. Just imagine you're sitting in a chair and the chair suddenly breaks. It is going to be a catastrophe. You're riding a bike, suddenly the wheel breaks. It is going to be a catastrophe, right? So we want to use only those elements which will give us fair amount of warning before failure. You're riding a bike, the wheel of the bike, it is getting deformed. You will get to know something is problem, you have to get the wheel repaired. Or if there is any problem with any other element, it will make sound, you will definitely take it to the garage. They will find out where is the problem and they will replace it. So ductile materials will be used in machine design, because we are now studying design of machine elements. Most of the things, almost 99% of the things will be designed using brittle materials, right? But you should know what is the criteria, what is the strength criteria used for designing of materials. What is the strength criteria used for designing of materials? Okay, you should understand this now. If the material you're using is brittle, the strength criteria is ultimate strength. For brittle material, we use ultimate strength, and for ductile material, we are going to use yield strength. SYT. Yield strength in tension. Is it clear, all of you? Is it clear, all of you? So for brittle materials, we are going to use ultimate strength, and for ductile materials, we are going to use yield strength for design. Okay. Abhi, what are the things that we got to know? First of all, first of all, for ductile materials, okay, for ductile materials, okay, let us, for example, let us see this. Okay, what are the different types of failures? Failures can be classified into brittle failure and ductile failure. Failures can be classified into brittle failure and ductile failure. So what is brittle failure? Brittle failure is the direct separation of the particles without appreciable elongation. बहुत ज़्यादा elongation होता नहीं है before failure. Not much strength, not much strain will be produced. Not much strain will be produced before elongation, before fracture, right? Not much strain. The strain portion is very less. The strain is very less. The strain is very less. But for ductile material, you can see there will be appreciable amount of inelastic elongation. You see, if you see, please focus, all of you guys, please focus here. If you see this elongation, ये तो थोड़ा सा आपको दिखाने के लिए बना दिए, just to show you that yield point. If you see the actual curve, if you want to see the actual curve, do you know how the actual curve will look like? Do you know how the actual curve, stress strain curve of aluminium will look like? It will be something like this. So you see, this is the non-elastic region. This is the non-elastic region. This much of strain, you can see it is in non-elastic region. This much of strain is in non-elastic region. The rest, all of them are elastic. Sorry, this is the yellow portion you can see is the elastic region, and the rest of the blue portion you can see is the non-elastic region. So most of the elongation happens in the non-elastic region. Elastic region में ज़्यादा elongation होता ही नहीं है. Most of the elongation happens in the non-elastic region, right? So you have to understand this fact. For ductile materials, there is appreciable inelastic elongation. Okay? For brittle materials, okay, this how the brittle material will feel. If I try to draw the stress strain curve of a brittle material, let us see. If I draw the stress strain curve of a brittle material, how will it look like? It will look like something this. Failure. Can you see? Just failure. So amount of elongation before failure is very less. The amount of elongation before failure is very less. So brittle failure, there will be direct separation of the particles without any appreciable elongation. Okay. Till now, is the points clear? Okay, abhi to basics hai. I think this much you might have studied even in strength of materials to some extent, but I'm at least briefing you whatever is required for this chapter. At least I'm briefing you whatever is required for this chapter. Okay. This much of knowledge should be clear. Others, is it clear? अगर clear नहीं है तो if you don't speak up, then it's not going to be possible. If you're not speaking up, it will not be possible. Good, fine. So how does the brittle material feel? Take a brittle material, if you suppose this is a material, this is a brittle material. You apply some load here. You apply some load here. If it fails, how exactly it is going to fail? How exactly it is going to fail is something like this. This is known as cleavage failure. This is known as cleavage failure. Cleavage failure. Right? So failure has taken place in the plane perpendicular to the direction of loading. Cleavage failure, the failure has taken place in the plane perpendicular to the direction of loading. right? And this will be a very sudden failure. Sudden failure. You will not get any warning. It suddenly fail. It will suddenly, instantly fail. What about ductile materials? If I talk about ductile materials, so what will happen? What will happen in ductile materials? If you take this stress strain curve, it will not yield till the yield point, and after the yield point, you'll have the lower yield point, higher yield point, and ultimate strength. And after ultimate strength, what will happen? Necking will start, right? From ultimate point, this is the ultimate point, SUT, and this is the fracture point. What will happen? Here the necking will start. So what is this necking? For example, you're loading it, you're loading the material, हमें थोड़ा सा फास्ट जाना पड़ेगा because you know the time we have is not much. ठीक है? I will not be able to go into each and every detail. ठीक है? So once you have started loading, what will happen? First, it will elongate. Then it will reach the SUT region. After that, necking will start. What is necking? This is the material will behave in like this. It will become something like this. So at the weakest region, so there will be some weak region here throughout the material. It will not be homogeneous. Some amount of difference in material properties will be there. So wherever their properties are weak, there this kind of neck will happen. And finally, if you keep on loading, what will happen? The failure that you are going to witness is a cup and cone failure. The failure that you will notice is a cup and cone failure. The failure you are going to notice is cup and cone failure. Cup and cone failure. Right? So in which direction this failure is happening? The failure is happening in 45 degree. Failure is happening, you can see failure is happening in this plane. Right? The failure is happening in which plane? You can see the failure is happening in this plane. Are is plane mein hai na failure? Whereas in brittle material it was happening in this plane. Brittle material it was happening in this plane. Right? So for brittle materials, they're failing perpendicular to the load. The brittle materials, that is brittle failure, is perpendicular to the load, whereas the ductile failure, it is at 45 degree angle. It is at 45 degree angle. Okay, so this is about ductile failure and brittle failure. So brittle failure, it is sudden in nature and it is known as cleavage failure, right? The failure will be perpendicular to the loading direction. So 3 points to be noted. Questions can be asked from all 3 points. About ductile failure. So ductile failure, before ductile failure, there is appreciable amount of inelastic elongation, means lot of deformation, lot of plastic deformation will be there for ductile failure. For brittle failure, there won't be much of plastic elongation, right? For ductile failure, a lot of plastic elongation will be there, right? Plastic deformation will be there. Secondly, the type of failure is a cup and cone failure. The type of failure in ductile materials is cup and cone failure. And the direction of failure, the third point, the direction of failure is at 45 degree angle. Direction of failure is at 45 degree angle to the loading. Okay, to the loading. Okay, so these are few points with respect to failure. Okay, these are few points with respect to failure. Now you must have a little bit of idea. I know this is a topic which can be I can keep on discussing. Okay, but again I'll not, because we have lot of things to cover. Okay, now you've got a little bit of idea about failure, right? There are 2 types of failure, brittle failure and ductile failure. And you also got to know that for machine elements, we are going to use ductile materials. And for ductile materials, what is the failure criteria? We will not wait up till the fracture. Fracture tak wait nahi karenge. We will not wait up till the fracture. If the ductile material is stressed beyond the yield point. If the ductile material is stressed beyond the yield point, we will consider failure has occurred. So what is the criteria for ductile material? Failure of ductile material, that is S, yield in tension. Okay. And what is the criteria for brittle materials? Strength, S, C. Or you can say ultimate, S, U, T. This is for brittle, and this is for ductile. Ductile failure and brittle failure. Okay. Now, my dear friends, now listen to me very carefully. Okay. Now, all of you, please listen to me very carefully. Right? So, this is what we have learned about failure. What is a failure? Okay. What is a failure and what are different types of failure? Now, what is theory of failures? Now, I do separate chapter theory of failures. Right? Now, till strength of materials, most of the things what you have seen, okay, most of the things we have done in strength of materials is something like this, that this is a member. We have loaded this member. So what is the stress generated in this member? The stress generated is force divided by the area, and this stress should be less than SYT for ductile materials, or less than SUT for brittle materials. This is what we have seen. Member है, member को load किया, so the stress generated, that is P by A, the stress generated, that is force divided by area, should be smaller than SYT for ductile material and should be smaller than SUT for brittle material. This is the criteria we know, right? But in a machine element, is it that only one kind of load like this will act on the member? No, definitely not. There are so many different combinations possible, right? There are 3 different directions. So load can be in all 3 different directions. Again, the load can be compressive in nature, tensile in nature. One load is compressive, the other is tensile, the other is compressive. That is also possible. You have shear loads also. You can also apply shear loads, right? So when under complex loading, we can say complex loading. Okay? This is what we can say is a complex loading. Complex loading means this is a simple loading, uniaxial. Uniaxial loading means only loading across one axis. एक ही axis के along loading है, right? That is the x-axis. This loading is along one axis, right? But if we talk about complex loading, right, or you can say multi-axis loading, okay, triaxial loading, biaxial loading, right? So there are different kinds of loads that can be applied, right? A lot of combinations are possible, right? It is seen that the materials, they fail much early, especially the ductile materials. They fail much early than this. Load itna पहुंचा ही नहीं, the stress has not even reached near to this, even near about 60%. The stress is about, it fails somewhere around 60% or even below. Right? When the stress generated is 60% of SYT or even below, the material is failing. So scientists were unable to figure it out. Why is it happening? Right? The strength of materials is giving us enough information, right? Enough logic, enough formulas to give us the answer. But still, practically when you're going to do this, okay, it is not matching the theoretical answers. The theoretical answers and the practical answers are not matching, right? So that's why the scientists, what they did, they started digging deep into it. They started doing research. They, through experiments and theory, definitely through experiments and theory, all the theories has to be complemented using experiments while doing research. And they put forward different theories why the materials are failing at different stress level, much below than the yield strength. Specifically, what we are talking about is ductile materials, because इतना ज़्यादा machine elements में हम लोग we don't, for brittle materials we don't do so much of study. ठीक है, brittle materials का एकदम direct फंडा है. It's a direct funda. If you are reaching the almost the ultimate strength, if you're reaching the ultimate strength, okay, it will fail. Okay, if you're reaching the ultimate strength for brittle materials, it will fail. So for brittle materials, we'll provide a good amount of factor of safety and we will design it. Okay. But for ductile materials, it's very important analysis and try to predict the results. Okay. Try to predict the results. Okay. And you can continue. What are the reasons? अभी continue कर सकते हैं. If you keep on continuing, ठीक है, अभी class खत्म नहीं होगा today. ठीक है. So let us see the various theories of failures that had been proposed by different scientists from time to time. Okay. So this theory of failures are dated back up to 1800th century. इतना पहले. This theory of failures were predicted as back as 1800th century. So old these failures are and still they are being used. Okay. The first one is the maximum principal stress theory. The first one is the maximum principal stress theory. तो यहाँ पर एक क्वेश्चन आता है, right? Sometimes you might be given maximum principal stress theory, or you might be given the name of the scientist who have done the majority of the work on this theory. Okay. So maximum principal stress theory, it is also known as Rankine theory, because Rankine was a scientist, the engineer, right, who actually worked the maximum, who contributed maximum to this theory. Okay. So this is the oldest. Maximum principal stress theory is the oldest. Let us see what exactly it tells. Okay. It tells us that permanent set. What do you mean by permanent set? It is permanent deformation. Okay. Permanent set is nothing else but permanent deformation, right? Permanent deformation takes place under a steady complex stress. Complex stress means it is not a uniaxial loading, it is multi-axial loading, where there are more number of loading directions. Okay. It is a mixture of all tensile, compressive, and shear stresses in all different directions. So according to this theory, permanent set, that is permanent deformation, takes place under a steady complex stress when the value of principal stress is equal to that of the yield point stress. So all of us know about the principal stress. Whenever there is a loading, in a member, there is stress, that is sigma 1, that is, suppose we have three types of stress, sigma x, or suppose a machine element has three types of stress, or even four types of stress. We are talking about biaxial stress. Okay. Sigma x, sigma y, and you have tau xy. Right? There are three types of stress. Okay. Because of this, these are not the maximum stress. Okay. These are not the maximum stress. These are the applied stress in x direction, y direction. So what are the maximum stress? We know there is sigma 1, which is the major principal stress. Then we have sigma 2, that is the minor principal stress. PAL. Sorry. Right. So how are the sigma 1 and sigma 2 calculated? Right. Sigma 1 is equal to, ये आपने किया है? Is it done? I don't know, because the time available is very less. If it is done, I will not do it. Anyways, I can just give you the formula. What is sigma 1? Sigma 1 is equal to sigma x plus sigma y. There are two different formulas. I am giving you the easier one, plus root over. Is it done? Good. Sigma 1 minus sigma 2 Okay, all of us know the formula. In that case, all of us know the formula. Okay, we'll not go through the formula. Okay, so what does this maximum principal stress theory says? It says that the maximum principal stress should be less than the yield stress in tension. Now, what we are talking about here, we are more inclined towards ductile material. Okay, that's why I have used SYT here. Why I have used SYT? Why I have used YT? Because we are considering ductile materials. And you should know now that why ductile materials? Because in machine design, in designing of machine elements, ductile materials is what we use. Okay, so every time we are going to talk about SYT in machine design, unless and until specified. Okay, so basically, sigma 1, that is the maximum principal stress, should be less than SYT, that is the yield strength in tension. Okay. Then we also divide it by factor of safety. We have a factor of safety, and this factor of safety, it depends upon the designer. Better the designer, better the factor of safety, he will be able to use it. Okay. Better the designer, better the factor of safety, he will be able to use it. Okay. Now, this theory has some limitations. Okay. This theory has some limitations. What are the limitations? This theory has some limitations. First of all, you can clearly see that this theory is just talking about sigma 1. This theory is talking about sigma 1. So it is not considering the other principal stress. Which is the other principal stress? That is the minor principal stress. It is not considering the minor principal stress. Secondly, it is ignoring shear stress. इस formula में shear stress है ही नहीं. There is no role of shear stress. So it is also ignoring shear stress. Okay. So disregards. What are the limitations? Disregards sigma 2 and tau max. What is the maximum shear stress? It is not paying much attention to that. Okay. Secondly, it is not working on hydrostatic stresses. It does not give good results. You know what is hydrostatic stress? You can't hear my voice? Is it so with everybody? Can you hear my voice, all of you? Can you hear my voice? Harini, you can try to reconnect once. You can try to reconnect once. So these are all one-liner questions that I'm talking about. Okay, these are all one-liner questions that I'm talking about. Okay, so I'll give you all different possibilities. Okay? You will not get any question out of what I'm teaching, at least for this chapter. Okay, so the second is that it does not give good results for hydrostatic stress condition. Okay, इसके लिए good results नहीं देता है. Finally, which is the deciding point, that is, what it says that a material will fail if you ignore the factor of safety part. The factor of safety will be there everywhere. Okay, a material will fail when the stress will be near about SYT. This is what it is saying. Basically, it is ignoring Tomx, but it is seen that when sigma 1 is near about, means the maximum stress is near about 0.57 to 0.6, failure happens. Means I'm not talking about sigma 1. When the sigma 1 has not reached its highest position, okay, somewhere between 0.57 to 0.6, failure happens. Right? So if that is the case, then we cannot use it. Okay? If it is not giving us the good results, then we cannot use this. Right? So that is why the next theory was developed, that is the maximum shear stress theory. That is why the next theory was developed, that is the maximum shear stress theory, because it has been found practically. Okay, theoretically, Rankine ne to bol diya. Theoretically, Rankine said that when sigma 1 is below SYT, material will not fail. Theoretically, Rankine said that he has done some experiments and he has done some theoretical work and he has proved that when sigma 1 is smaller than equal to SYT, the material will not fail. Right? But it has been seen that when sigma 1 is equal to 0.57 to 0.6, failure happens. And this is not going. This theory is not very true. Right? However, this theory can be applied, gives us good result for brittle materials. It gives good result for brittle materials, satisfactory results for brittle materials. Good for brittle materials. Is good for brittle materials, but for ductile, we are not going to use it. Okay? But for ductile materials, we are not going to use it. Why? Because, again, I'll tell you why. Because I don't have the time to get into all the details. But why? Because you might be knowing, okay, ductile material fails because of sigma 1. That is the maximum principal stress. Whereas the brittle material fails because of the sigma 1. We know in which direction the brittle material fails. Last उसमें देखा था, right? Brittle fracture, it is perpendicular to the loading. This is because of the sigma 1. This is nothing else because of sigma 1. However, the ductile materials, they fail because you have seen, it undergoes cup and cone failure. Right? This cup and cone failure is because of shear stress. The shear stress is maximum at 45 degrees. Shear stress, in this case, in uniaxial loading, it is maximum at 45 degrees. And this one, maximum principal stress theory does not take into account the shear stress. That is why we cannot use it. We should not use this theory for ductile materials. For brittle materials, we can use it. Right? So what are the type of questions that are being asked? यहाँ पर a simple example, ठीक है? For example, maximum principal stress theory can be applied to option A, brittle materials, option B, ductile, option C, both ductile and brittle material, option D, none of the above. So you now know what will be the answer, right? Maximum principal stress theory. Maximum principal stress theory is good for which kind of materials, right? Brittle material, ductile material, both brittle and ductile, none of these. Okay? A simple question, that kind of question can be asked. Okay? The second question that can be asked is, okay, is it taking care of Tomax? No, It is not taking care of Tomex. Is the sigma 2 and Tomex being considered in maximum principal stress theory? Okay. Third question that can be asked is this formula itself. The third question that can be asked is that formula itself. Okay. इसमें numerical आने के chances बहुत कम है because it is a very simple numerical. This is simply directly from strength of materials, right? This is directly from strength of materials. Okay. So generally they will not ask you any numericals for this, right? Now, why this theory is not preferred? Why this theory is not preferred? Because failure is happening at a much lower strength than predicted by this theory. For ductile materials. For ductile materials, the failure is happening at a much lower strength. For ductile materials, the failure is happening at a much lower strength than that of the strength predicted by this theory. Okay. So, are you getting it? What are the things that you need to remember? We'll summarize it. We are going to summarize it. Okay. You need not worry. We are going to summarize it. Okay. Whatever things you have to see. So that's why the new theory came up. That is a maximum shear stress theory. That is a maximum shear stress theory. This is the new theory that came up. That is the maximum shear stress theory. So what does this maximum shear stress theory say? Okay. Again, this is being worked upon by three different scientists. They have contributed at different times and from different countries. They were from different countries and they were also separated by good amount of time. But these are the major contributors. These are the major contributors to this theory. Guest, Tresca, and Call. So instead of maximum shear stress theory, they might also call it Tresca's theory or Coulomb's theory or Guest theory. Okay. So you have to remember this name of the scientist also. Okay. So what does this theory say? According to this theory, a specimen subjected to any combination of loads. So combination of loads is nothing else but the complex load is talked about, right? What is complex loads? Complex load means more than one loads acting in different directions. Okay. When the maximum shearing stress at any point reaches the failure value. So what does it say? It says that okay, when a specimen is subjected to any combination of loads, failure will occur when the maximum shearing stress at any point reaches the failure value. So that is, I can say, this equation. Tomex, or better to say, instead of equal to, I should use a greater than, smaller than, equal to sign. I should use a smaller than equal to sign, right? Tomex should be smaller than equal to the SYS. This is what I'm talking about. Tomex, maximum shear stress. Maximum shear stress should be smaller than equal to SYS divided SYS. Yield strength in shear. Yield strength in shear. Now all will use a factor of safety. Designer point of view, I'm making this formula as such because it will help you in answering the questions, numerical questions if they're being asked. So SYS divided by factor of safety. All designers will use some amount of factor of safety. Okay. This factor of safety, again, how big the number will be or how small the number will be, that is dependent on the quality of the designer, how good, how experienced the designer is, right? If you're keeping the factor of safety very high, those designs will be very conservative, right? The structures will be big, heavy, right? Uneconomical, right? Lot of money will be required because you're using high factor of safety means all the structures will be very, very big, right? Whatever you're making will be very, very big, right? So cost will also increase. If you're using a low factor of safety, what will happen? If you're using a low factor of safety, your design will be at risk. There is a probability of high failure. Okay? No doubt the cost will come down. The cost of the overall production will come down, right? But you might again have you might be compromising on the safety aspect, okay, of the failure aspect. You might be compromising on the failure aspect. So a good designer is one who is able to balance both sides, okay, using an appropriate factor of safety based on his experience, right? Which is neither very costly, there is not very high factor of safety, neither very low factor of safety, right? Now, according to this theory, SYS shear is equal to SYT divided by 2. All of you please remember this. This is a very important relationship. ठीक है, ये आपके डायरेक्ट क्वेश्चंस में भी आता है. डायरेक्टली द क्वेश्चंस they ask directly in questions also. Okay, and many where you might be able to apply it. So if that is the case, so this will simply become smaller than equal to SYT divided by 2 into factor of safety. SYT divided by 2 into factor of safety. Right? So Tomex, I can directly write now, Tomex is smaller than equal to SYT divided by twice of factor of safety. Now, do you know what is the formula for Tomex? You might have already been seen Tomex, sigma 1 minus, I can say this way, maximum of, if I write the whole formula, maximum of sigma 1 minus sigma 2 divided by 2, comma, sigma 2 minus sigma 3 divided by 2, comma, sigma 3 minus sigma 1 divided by 2. So the maximum of all these threes will become the maximum shear stress. If I'm talking about biaxial loading, means only two principal stresses are there. Okay? I'm talking about biaxial loading. What is the biaxial loading? This kind of loading is known as biaxial loading. So if you have stress only in two directions, so mostly questions will be from biaxial loading. Triaxial loading, thoda sa, it becomes out of your scope because time allotted per question will be very less. So this is biaxial loading, right? Loading only in two directions. So loading is only in two directions. So we don't have the sigma 3. Okay? We don't have sigma 3. So in that case, what I can say that Tomex, I can write it as sigma 1 minus sigma 2 divided by 2. Are bolo, yes or no? Are you following? Sigma 1 minus sigma 2 divided by 2 SYT divided by 2 times factor of safety. So 2 will cancel out. So I can simply write sigma 1 minus sigma 2 should be smaller than equal to SYT divided by factor of safety. So this is the second equation we have with us. This is the second equation that we have with us. I've got Prabhakar and Naveen, they're saying, what about Guna and Aravindan? And I think one person is not there. Okay, good. Okay, so we can write it as sigma 1 minus sigma 2 is smaller than equal to SYT by F4S. So whichever equation you want to remember, you can remember. Okay, whichever equation you want to remember, you can remember. That is up to you. Okay, if you know this part, you can directly remember this, or better to remember this. And if you know this portion, that is, it will be good. Better to remember this portion. Better to remember this portion, and separately you remember this. Okay, that is better to do instead of directly remembering the formulas. It is always better to approach it through the basics. Now, so is this theory good? Yes, this theory, it is good for brittle materials. It is good for brittle materials. This theory is good for brittle materials. Good for brittle materials. Gives satisfactory result. Okay, satisfactory result for brittle materials. Okay. Oh, sorry, no, I'm not saying brittle. No, not brittle. Sorry, ductile materials. Is good for ductile materials. Okay. So gives satisfactory result for ductile materials. It gives satisfactory result for ductile materials. Okay. But still, there is still chance of improvement. Why there is a chance of improvement? As you can see here, the ratio SYS by SYT. This point I'm talking about. I'm talking about this point. This point I'm talking about. What is the ratio of SYT by SYS by SYT? So this is again being asked. Okay, na? एक ध्यान रखिएगा, this is again being asked. It is equal to 0.5. Through experiments, it has been found that on an average, it should be around 0.57. Through experiments, it has been found that on an average, right, the ratio of SYS by SYT is somewhere around 0.57, right? But still, it is giving a satisfactory result. Rest of the things we can compensate using a higher factor of safety. एक higher factor of safety हम use करके, by using a higher factor of safety, we can compensate the error. So what is the percentage of error here? You can see there is almost a 10 to 15%, around 15% error. 15% error. So practically, physically, this is what is the actual. Okay. So if you're asked, so I'm again telling you a question. What kind of questions can be asked? Okay, what kind of questions can be asked? First of all, it might be asked, maximum shear stress theory can be applied to brittle material, ductile material, both brittle and ductile, none of non-brittle and ductile, none of brittle and ductile. ठीक है, तो आंसर क्या होगा? Ductile, right? Which portion you want me to zoom? This portion? Right. Okay. Secondly, what is the ratio as predicted by maximum shear stress theory? Or in place of maximum shear stress theory, what they can say? They can say according to Tresca's theory or Guest theory or Coulomb's theory. Right? According to Tresca's theory or Guest theory or Coulomb's theory, what is the ratio of SYS and SYT? That is, what is SYS? Yield strength in shear. What is the ratio of yield strength in shear and yield strength in tension? So what will be the answer? 0.5. What will be the answer? 0.5. Okay. If nothing is mentioned, yes, good Prabhakar. Good Prabhakar, good Guna. So what is, if nothing is mentioned, suppose no theory is mentioned, if simply you are being asked, what is the relationship between SYS and SYT? That is, what is the relationship between yield strength in shear and yield strength in tension? Then you can write 0.57. If no theory is being mentioned, then you will write 0.57, right? Generally, but this is what we generally consider for most of our designing purpose. For most of our designing purpose, we consider this because it is convenient. Again, it is convenient to design using this. Then what we do, you use a higher factor of safety. Our factor of safety, जो भी थोड़ा सा 15% का error है, whatever error is there, it is compensated by the factor of safety. Okay. So I hope it is clear. Is this slide clear to all of you? Give me a yes if it is clear. Prabhakar says yes. Naveen says yes. What about the other two, Guna and? Okay. Very fantastic. So do you feel I'm going a bit slow? Should I increase my pace? Naveen is saying yes. What about others? Should I increase my pace? The first class, so I have to know. You're finding the pace okay? Other two? Okay, fine. Okay. So let us try this problem. Let me see. Are you able to do it or not? Try this problem. Or if you try this problem, tell me when you are done. Otherwise, you anyways have 1.5 minutes more. Try it. After that, I will try to solve it for you. We found the answer to be B. देखते हैं, ठीक है? Let us see. Let us see. So we'll go by the basics. ठीक है, एक बार basics से हम जाएंगे. So what is the state of stress given to us? Sigma x is equal to 100 Newton. Sigma y is equal to 40 Newton, and tau xy is equal to 40 Newton. Okay. So this is sigma x, sigma y, tau xy. So first we have to calculate the principal stress. ठीक है, आपको ये formula याद होना चाहिए. This formula is the most important formula. ठीक है, this formula you can see sigma 1 minus sigma 2 by 2, or what you can do, I generally prefer to remember this formula. Because I find it easier and conceptual. Okay, this is more conceptual. The more the number of formulas you try to remember, so it's get difficult. Okay. Okay. So I have to calculate tau max. Right? So what is tau max? I know it is sigma 1 minus sigma 2, maximum principal stress, that major principal stress minus minor principal stress divided by 2. This is nothing else but tau max, the maximum shear stress in this point, right? Again, what is the formula for sigma 1? Sigma 1 is equal to sigma x plus sigma y divided by 2 plus root over sigma x minus sigma y divided by 2 whole square plus tau xy whole square. And what is the formula for sigma 2? Sigma 2 is equal to sigma x plus sigma y divided by 2 minus sigma x minus sigma y divided by 2 whole square plus tau xy whole square. So from here, if you want to calculate tau max, okay, can I say tau max? Or can I say that tau max if I simply do sigma 1 minus sigma 2 divided by 2? See this portion, this will get cancelled out when you're subtracting, this will get cancelled out. So this is plus, minus a minus sign will become plus. Okay, so 2 times of this part, 2 times of this part divided by 2. So can I say what is sigma max? Sigma max is nothing else but, अरे बोलो, sigma x is nothing else but sigma x minus sigma y का whole square plus tau xy का whole square. This is the formula for sigma max. Yes or no? Right. So can you now calculate the sigma max? Then tell me what is the sigma max value? Tell me what is the sigma max value? Can you now tell me what is the sigma max value? अरे formula में put करो ना numericals. Put the numbers. Put the value of sigma x, sigma y, and tau xy. Tell me what is sigma max. Fantastic. Very good, Naveen. Others also fast. Others, have you got the answer? Good. Now proceed on to the formula. You see what is given in the equation. What is given in the equation? The yield strength is given. So put in the formula. You have the formula. And give me the factor of safety. Don't expect me to do each and everything for you. But that way, you will not improve. Try to think. Go back to the formula. See how to use the formula. What are the values given? What values we have found out? And how to find out the factor of safety from there. Very nice, Naveen. Very nice. Very nice, Guna. Very nice, Ravindan. Prabhakar, are you getting it? Fantastic. You substitute the values here, you will get Tom X is equal to 50 Newton. It is not Newton, sorry, Newton per mm square, megapascal. स्ट्रेस का यूनिट न्यूटन नहीं होगा, मेगापास्कल. Tom X is equal to 50 megapascal. Now you see here in this question, it is already given yield strength is given. What is given? That is why it is very necessary to know the basics. Yield strength is given. So if yield strength is given, can I directly use this formula? जो ये formula directly use करता है उसका गलत हो जाएगा. You cannot directly use this formula. And why I have derived this formula? There is logic to this. Okay, there is logic to this. We are going to see why you have derived this formula. Okay, but directly use formula को use करें. Only the blue part. You can see Tom X is smaller than equal to SYS by factor of safety. Okay, what is Tom X? Tom X should be smaller than equal to SYS divided by factor of safety. That is 50 smaller than equal to SYS is given as how much? 300 to 50. अच्छा, it is not given yield strength in shear नहीं दिया हुआ है ना, तो yield strength दिया हुआ है SYT. It is not SYS, it is SYT. Yield strength. It is simply given as yield strength. It is simply given as yield strength. Sorry, it is simply given as yield strength. If it is yield strength, means it is yield strength in tension. So you can directly use this formula in that case. Okay, if it is given in yield strength, I thought it is given yield strength in shear. No, yield strength. So I'll have to write it this way. I'll have to write it this way. Tom X is equal to, or better to say, smaller than equal to SYS divided by factor of safety. So this is equal to smaller than equal to SYT divided by 2 times factor of safety. So this is what is given. So 50 is smaller than equal to 300 divided by 2 times factor of safety. So factor of safety equal to 3. Right? Okay, good. So it is clear to all of you. Fantastic. So similarly, but as I said you, this is also not the precise, right? Why? Because it is still having 15% error. There's still chance of improvement. There's still chance of improvement because it is giving the ratio of SYS by SYT as 0.5, but practically it is found to be 0.57. right? Still it has little bit of scope to improve. Okay? Still it has little bit of scope to improve. So basically this is more conservative. This formula is more conservative. Later on we are going to understand. Okay? This, what do I mean by that? Later on we are going to understand when we will compare all different theories. So the third theory came, that is the maximum distortion energy theory. It is also known as maximum shear strain energy theory. Shear strain. Okay? Distortion is nothing else but shear strain. Okay? And who gave it? Haber, Hanke, von Mises. So many times you might not be said maximum distortion energy theory. You might be simply said von Mises theory. Which of the following theories are applicable to ductile materials? Guess theory, Rankine's theory, von Mises, or none of these. ठीक है, इस तरह के क्वेश्चन होगा तो you must remember both the name. You must be remembering maximum distortion energy theory and also strain energy, shear strain. This is shear strain, and then von Mises. Okay. So according to this theory, do you know what is shear strain? All of you know what is shear strain? All of you know what is shear strain? Normal strain, all of you know. I know that. Normal strain, all of you know. What is normal strain? Normal strain is equal to change in length by original length. This is the normal strain. Normal strain again can be divided into two parts, transverse. Okay. What about shear strain? Do you know what is a shear strain? Yes or no? You guys don't have much idea about shear strain, it seems. People are silent. So let us try to understand a little bit about shear strain to whatever extent possible. So this is a member which is fixed, let me say at ground. This is a box. Okay. Change in volume नहीं है. There is not change in volume. Okay. Change in volume is hydrostatic strain. Change in volume by original volume. Volumetric strain, you can say, or hydrostatic strain. Okay. Dilatation. Okay. That is different. Suppose you apply a force. अभी ये courses जो है ना, these courses are long courses. Okay. We are trying to give you the maximum amount of input in such a short time. Okay. So definitely need not be sorry. Yeah. Okay. The thing is that you must improve. You must keep on improving yourself. Okay. A lot many things to learn. So in a very short period of time, we are trying to give you the maximum amount of information so that you can at least do better in the HL exam. So suppose you are applying any force here. Okay. So this force will become a CS. If you see this cross section, if you take this cross section, this force is basically a parallel to this cross section. If you're taking this cross section now, let me try to draw the full. Then we'll convert it into 2D. Suppose this is what you're talking about. Okay? So if you're talking about the cross section, if you're talking about this cross section of the box, suppose you're talking about this cross section of the box, this cross section. So what kind of load is this? This is a shear load. Why shear load? Because this load is parallel to the cross section. This load is parallel to the cross section. So any load, if it is parallel to the cross section, then it becomes a shear load for this cross section. For this cross section. So this is a shear load for this cross section. Now, थोड़ा सा समझ लेते हैं हल्का सा, so that you get a little bit of feeling. I cannot go into much deep. Okay. Now, what will happen because of this shear load? Definitely some amount of strain will be there. Okay. This is fixed. The ground is fixed. So what will happen if you apply the load high enough? Okay, there will be slight change in the orientation. So this box will slightly change to like this. ज्यादा तो नहीं, लेकिन थोड़ा सा ऐसा इसका शेप चेंज हो जाएगा, right? It will slightly change its shape because of this force. Okay. Yes, because of modulus of rigidity. Modulus of rigidity again अलग चीज हो गया. What is modulus of rigidity? That is the ratio of shear strain to shear stress. Okay, sorry, shear stress to shear strain. What is modulus of rigidity? That is shear stress to shear strain. Yes. Okay. Because of this, okay, because of this, okay, there will be slight change in the shape. Okay. So you can see there is a change in shape. Okay. I'll not go into all formulas and all. I'll not try to confuse you in a very little time to give you overloaded by making you information overloaded. But you can see what kind of change is there. One thing we know for sure, that strain is change divided by the original. The change divided by original. So what kind of change can you see here? Tell me. Can I say the block has undergone change in shape? Yes or no? Earlier it was square and now it is no more a square element. If you see one-sided, if you see from whatever view you're looking at, right? So what kind of change it has gone? If you take this one, if you take normal strain, what kind of change will see in normal strain? You take this member, then you load this member, you'll be able to see the change in its length and breadth. Shape तो same है ना, पहले भी rectangle था, अभी भी rectangle है. If you load it this way, initially also it was rectangle and finally also it is rectangle. Right? What has changed here? There is a change in length. So this is what is represented by the normal strain or transverse strain. Okay? But for shear strain, it is slightly different. So what is shear strain all about? Shear strain is all about, you can see on application of this load, the member has changed its shape. The member has changed its shape. So shear strain is all about change in shape. Shear strain is all about change in shape. Okay. So let us go inside this theory. I hope you have understood what is shear strain. Now, according to this theory, the portion of strain energy, again, let us see a little bit of strain energy. What exactly is strain energy? Okay, what exactly is strain energy? You know what is strain energy properly? All of you? You know what is strain energy? Yes or no? Good. Prabhakar is saying yes. Others are a little bit silent. Okay, good. You know what is strain energy. So whenever there is some amount of deformation, and I'll not go into detail, when there is some amount of deformation, the energy that is stored inside, right? That is because that is the strain energy, right? Okay. Now, according to this theory, the portion of strain energy producing the change in shape of the element is assumed to be completely responsible for the failure of the material by yielding. ठीक है, अभी बहुत ज्यादा अंदर नहीं जाता है, ठीक है ना, बहुत ज्यादा समझने की कोशिश नहीं करते इस चीज को, because in normal class also you will be taught, but not to very detail. उतना ही पढ़ना चाहिए जितना अभी जरूरत है according to our exam. ठीक है, we will not try to do PhD here. ठीक है, when it is right, Avirandan, right? Aravindan, sorry, Aravindan, very nice name, very unique and nice name. So shear strain is because of change of shape. So what it is saying, what is this theory saying? Why it is saying, we will not go into that. Why it is saying that? Usme fir explaining you will take another 15 minutes. The portion of strain energy producing change in shape. So change in shape means nothing but shear strain. It has another name, that is distortion energy. Shear strain, we call distortion. What is distortion? If I'm saying distortion, means it is changing the shape. अब मैं अगर बोलता हूँ, if I say that your face is distorted, what does it mean? Means the shape of your face is little bit, right? Somebody might have punched you, or you might have fallen down. It looks distorted, right? So that is nothing else but change in shape. So remember why I'm telling this, because to make a connect, okay, so that you can remember the things. So distortion energy, okay, strain energy producing change in shape of the element, right, is responsible for the failure of the material by yield. Okay? I'll not go into detail why it is saying that, बस अभी इतना तक ही समझ लेते हैं, ठीक है? What it is saying that the change in shape, the strain energy producing the change in shape, that is the shear strain energy or distortion energy, is responsible for failure of the material. Okay? We can derive this formula. Okay? We can derive this formula, but you have to remember this formula. Better to remember it. If you change it into 2D, in 2D means if you neglect sigma 3, you neglect sigma 3 SYT by a factor of safety whole square is equal to, I'm directly putting is equal to, I'm not more using smaller than greater than equal to. You can put that also. Okay? So this becomes half sigma 1 minus sigma 2 whole square plus sigma 2 square plus sigma 1 square. You can open this. If it is a two-dimensional, what I'm saying, it is a two-dimensional, for two-dimensional, for 2D stress, biaxial stress, I can write it at this way, right? I can simplify it even further. आप एक बार simplify करके, ठीक है, all you can write down your formula. You can simplify, because it is not necessary that the formula is asked. Okay? And this is the third kind of question that can be asked. You can telling all different type of questions that are being asked. Most of the question, 99% of the questions will be theoretical in nature, and it is covered here in this PPT, whatever in this class. Okay? So the question, this is for 2D. This is for two dimension. Okay? You can further simplify it. कोई दिक्कत नहीं, you can further simplify it. You simplify it and keep it. Okay, I'll not do it for you. For square terms, you have to do it. Okay. So again, these formulas are being asked. Okay, now you'll be given which of the formula is representing the maximum distortion energy theory, or Won's Mises theory, or the maximum shear stress, shear strain energy theory. Okay. So ये भी important है. Okay. What apart from this? Okay. What apart from this? So this again, it is not suitable for brittle materials. Not suitable for brittle materials. Second, this is the best theory for ductile materials. I'll tell you why. So this is the best theory for ductile materials. Okay. At last, I will relate all these things to you. Don't worry. Okay. Almost we are towards the end. Okay. And according to this theory, yield strength in shear is equal to 0.577 S by T. So this is why it is giving us a very, very accurate, very near result. It is giving us a very near result, very accurate result. That is why this theory is best for ductile materials. This theory is best for ductile materials. Okay. So which is the best theory? Again, I'll try to relate. From now, let me try to relate. All of you pay attention. Okay. Now, we have seen that brittle materials. Okay. For brittle materials, what is the type of failure of brittle materials? Brittle materials failure have a cup and cone failure, and that is because of shear stress. Brittle materials fail because of shear stress. Sorry, not brittle material. Again, let me repeat it. Ductile materials. Okay? We are mainly talking about ductile materials in machine design. Okay? Ductile material, they have a cup and cone failure. The failure is at angle of 45 degree to the longitudinal axis. And why does this ductile material fail? The ductile materials fail because of shear. If you can remember this, then you will be done with most of the questions. If you can remember this, then you'll be done with most of the questions. How ductile material feels? Ductile material feels because of shear stress. Okay. So wherever the shear stress term comes, definitely that will be good, right? So you see, this is shear strain. This is definitely good for ductile materials because the main shear is coming, right? How does brittle material feel? Brittle material feel because of tension. Brittle material feel because of tension. So for that brittle materials, the principal stress theory, maximum principal stress theory is applicable. Maximum principal stress theory is applicable. So whenever you're talking about brittle materials, just look for maximum principal stress. Why maximum principal stress? Because brittle material fail because of the principal stress, tension for brittle, right? Again, if you come to ductile material, why the failure happens in ductile material? The failure happens in ductile material because of shear. Okay. And we have already spoken that ductile materials fail the ductile in machine design. We will be using ductile materials, and you also know the logic why we are using ductile materials in machine design, right? Now let me tell you a question. Okay, all of you listen to the question and tell me. Okay, all of you listen to this question and tell me. Okay, which one of the theories of failure, will be used for designing a transmission shaft? Which of the theories of failure will be used for designing a transmission shaft? Options are maximum principal stress theory, option A is maximum principal stress theory, option B is maximum distortion energy theory, and there are two other theories. These are least important. Okay, maximum principal strain theory, you can see maximum principal strain theory, and then we have maximum strain energy theory. What should be the answer? ठीक है, अभी पूरा आपको बताया नहीं है what are these two. I have not even told you, but just looking at the name, you should be able to tell. Okay, your concept should be so good. So I'm designing a transmission shaft. I'm designing a transmission shaft. All of you are saying maximum principal stress theory. Now first tell me, a transmission shaft, it will be made of what kind of material? Will it be brittle or ductile? Brittle or ductile? Transmission shaft, it will be made of brittle material or ductile material? Why? What is the logic behind your answer? Is transmission shaft a part of machine? Yes or no? Is transmission shaft a part of machine? Yes or no? It is a part of machine design, right? In machine design, what kind of materials we are going to use? Are we going to use brittle material or ductile material? In machine design, what kind of material are we going to use? Ductile or brittle? Prabhakar is in ductile. What about others? Ductile use करेंगे, brittle use करेंगे? Initial half an hour, I have given you lecture on this. Tell me. We'll use ductile material, right? Because ductile material will give us sufficient amount of time before failure, before fracture. Failure will happen, okay, but failure will not cause a catastrophe because you'll have sufficient time before complete fracture. Okay, so in machine design, always remember we are going to, in this whole subject machine design, we are going to talk about ductile materials. Now, ductile material fails in, again, ductile material fails in shear or tension. Tell me, ductile material fails in shear or tension? Few points you have to remember. ठीक है, अभी पूरा लॉजिक में बिकॉज अभी इतना टाइम नहीं मिला है, ठीक है, अदरवाइज यू कुड हैव लॉग्ड ऑन टू दैट प्रिंसिपल स्ट्रेस मोर सर्कल, दैट चैप्टर clears all your concepts. ठीक है, clears all your concepts, but for now you'll have to remember a little bit. ठीक है, ductile material it fails in shear. ठीक है, always remember ductile material fails in shear. ठीक है, and what kind of failure is there? Failure is cup and cone. Cup and cone. And it is at an angle of 45 degree. Why 45 degree? Because shear stress is maximum at 45 degree. Maximum shear stress. Array, maximum shear stress is at 45 degree for uniaxial loading. For uniaxial loading, what I am talking about is uniaxial loading. Okay, and this is true for everybody. Okay, uniaxial loading hai, PP, maximum shear stress will be along this plane and along this plane at a 45 degree. That is why you are getting a cup and cone fracture. That is why you are getting a cup and cone fracture, because the fracture will happen here, na? So that is why you are getting a cup and cone fracture. So this is the linking. This you have to link. Transmission shaft is made up of ductile material. Ductile material fail through shear, right? What kind of failure is there? Cup and cone fracture. Okay. What is this cup and cone fracture? Where does it occur? Okay. You can see the cup and cone. You can remember it this way, na? The cup and cone fracture. This is the cup and this is cone. Why it is known as cup and cone? Because this side looks like a cup and this side looks like a cone. Cup and cone. So why is this cup and cone happening? Because maximum shear stress is at 45 degree. Because maximum shear stress is at 45 degree. ये सब क्लास में प्रूव किया जाता है. Generally in class we used to prove it, but you have to remember this for now. Okay? Because again these are important. Okay? With respect to all the different questions, right? Okay, is it clear now? Transmission shaft is a part of machine design. Machine design, we make it with ductile materials. Ductile materials fail in shear. What kind of shear failure? Cup and cone failure. What is the angle? 45 degree to the principal stress. Okay. So if ductile material fails in shear, so what theory we are going to use? We are going to use either maximum distortion energy theory, or because of this. Why? Because of shear strain. जहाँ shear आ गया ना, why I am focusing, why I am emphasizing on these words, so that you get the link. Shear means ductile failure. Ductile means shear failure. You should be able to link. So this is the best theory for ductile materials. If this theory is there in option, so definitely this is the option. अगर ये maximum distortion energy या फिर Hanke von Mises या फिर strain energy theory option में है for ductile materials, definitely the answer is this option. ठीक है? So I say ductile material. In place of ductile material, I can say transmission shaft. In place of transmission shaft, I can say gear. Now in place of gear, if I say which of the theories, अभी ये तीन नहीं बताओ, बाकी दोनों तो इतना important नहीं है, ज्यादा questions नहीं आते हैं. ठीक है, whatever you have learned till now. ठीक है, this is the first three are the most important, because most of the questions will be asked from this. ठीक है, next three I will definitely tell you, but it is not that important. The questions are not asked much from the next two. Though there are 5 theories of failure, first three are the most important failure theories. So distortion is the best for transmission shaft. Now, if I simply change the transmission shaft into gear, will there be any change? Now you know the logic. For gear design, which theory of failure you are going to use? Tell me. For gear design, which theory of failure you are going to use? Same logic. Gear. For gear design, which failure theory you will use? Same logic. Naam change ho jayega. Transmission shaft will become gear. But gear again, it is a part of machine design, yes or no? It is a part of machine, na? Machine means ductile. Ductile means shear. Shear means distortion energy. Okay? Shear means distortion energy theory. Okay? Now, if I change the gear into axle, if I change the axle into something as connecting shaft, connecting rod, whatever failure criteria, and if it is shear, okay, then this is the best theory. This is the best theory. Maximum distortion energy theory is the best theory. Okay. Now, suppose option does not contain this. Maximum distortion energy theory is not there in option. Then the second best is maximum shear stress theory. Because this is also shear stress, na? This is also shear stress, na? Good. This is good. Good for ductile materials, but not best. Which one is the best? Best one is the maximum distortion energy. But if option does not have maximum distortion energy, this is the second best. For ductile materials. Second best for ductile materials. Okay. And apart from that, it is principal stress theory. Okay. कोई भी brittle material है, if any brittle material is there, then we will go to use maximum principal stress theory. ठीक है. बाकी दोनों जो है वो कहीं नहीं आएगा. It will never come in any answer. Options में रहेंगे. ठीक है. It will be there in options, but it will not be the answer of any question. So this three will be the answers. ठीक है. I'll give you some variations also. ठीक है. I'll give you some variations also. So what will be your task today? Okay, now what will be your task today? I'll again do a little bit. You have that 880 PDF question paper, previous years. All of you have it, which is shared to you. Yes or no? A complete set of paper questions has been given to you now, which contains some 8,000 questions from all different JEE AE level papers. Yes, PSU PDF, right? So try to attempt all the questions from theories of failures. Theories of failure is there in strength of materials, and see, are you able to solve how much? Okay. Most of the questions you'll be able to solve it. After learning from here, most of the questions you'll be able to solve it. Okay. So what is next? Next is the maximum principal strain theory. You remember the formula बस बहुत है. Simply remember the formula, maximum principal strain theory. You remember the formula, that is good enough. Apart from formula, I'll tell you, it gives again because you see principal strain. Okay, principal strain means brittle materials. You have a meeting at 3. So ठीक है, हम इसको बंद करेंगे. We'll continue next class. ठीक है. अभी एक दो क्वेश्चन शायद आपको नहीं होगा, ठीक है ना, लेकिन otherwise you'll be able to solve it. ठीक है. Because we'll also have to take some rest, right? आप लोग का lunch हो गया? नहीं हुआ सर. I think we have exceeded the time ना. तो ठीक है, we'll do one thing. We'll end the meeting here today. Okay, we'll end the meeting here today. Next class, because I got late because I had to try. I get acquainted with the this one. Okay, so okay, no issues. You try and whatever is left out, okay, we will see next class. So definitely before your next class, okay, that will be on, I think, on Wednesday. Okay, we have the next class on Wednesday. You have 2 days time. So please at least go through the questions of theories of failure. Okay, at least go through the questions of theories of failure. Okay, okay, done. Thank you. Thank you. Thank you, all of you. I'll not be taking any new concepts now. If you have doubt, if you want to wait, then you can wait. Otherwise, you can leave. You can go for your lunch and you can be ready for your next meeting. Thank you. Thank you, all of you. Thank you. If you have any doubt, you can ask. Or if you want to go for your lunch or take some rest before your next class.